The purpose of this lab was to create a physical demonstration of inductance and measure its effects, and also to simulate this demonstration and compare the simulated results with reality. Some models used were Maxwell's equations, magnetic field of a current-carrying loop, and force due to gravity. The results of this lab was that the experimental time was measured to be about 1.11 seconds, and the simulated time to be 1.135 seconds. Some fundamental physics models used in more detail was the current carrying loop was used as the tube the magnet was dropped into is simplified into a bunch of current carrying loops, each which induced a magnetic field proportional to the current induced in it. The formula for this is mu naught I over 2r. This current came from Maxwell's equations, which shows that the flux of the falling magnet created a change in flux, which induced a current, which created a magnetic field, which applied a force back onto the magnet. The force of bringing the magnet down through the tube was the force due to gravity, and this was determined with the force due to gravity equations as seen on the right. The experimental setup is seen in the picture here, with the aluminum-wrapped tube being held vertically with a magnet positioned above it and a soft surface below it to catch the magnet. Off-screen is a camera recording this setup to determine the start and stop times. The magnet was allowed to drop through the tube, and the difference between the times of it entering and exiting was measured for the experimental results. The data was collected in the table on the left with an average of 1.11 seconds. Some other measurements collected from this setup was that the thickness of the aluminum tube was approximately 0.3 centimeters, the radius was 3 centimeters, and the length was 47.8 centimeters. These values were plugged into the glow script code that was created to simulate this experiment. Further edits to the glow script code was to create a magnetic field formula for a dipole magnet, which was used to model the bar magnet dropped into the tube. This was also used in consideration with the calculating the delta flux, which can be seen in the function below, where the radius and distance and speed of the magnet compared to the tube was used to calculate the change in flux using Maxwell's equations and the other equations and models we used before, giving a change in flux which can be used to calculate induced current, which can be used to calculate magnetic field back into the bar magnet, as discussed before. The glow script code gave a result which can be seen on the right, where the magnet initially drops in at a higher speed, levels off at around negative 0.15 meters a second, and drops out of the bottom of the tube with a total time of approximately 3.135 seconds. This does match reality, as there is an expected terminal velocity to be reached when the magnetic force back into the magnet balances out the force due to gravity, and these things are unequal, and 3.135 seconds is close enough to reality to accept the results on both sides. There are a lot of sources of error, which is why we can accept a difference of 2 seconds and a measure of 3 seconds. The tube used in the experimental was very poorly constructed. It was not a constant circular diameter. There were bits of aluminum peeling off, which could decrease the thickness in spots and allow less magnetic force propagating back into the bar magnet. There was manual measurement of the magnet dropping. Even though a phone was used for precision, there was not enough frames to get an exact entrance time and an exact exit time, which could add a little bit extra error. There's propagated error possible from Lab 4, since this mu is taken from experimental data acquired from Lab 4, and Lab 4 had a lot of issues which could have led to a faulty mu, which propagated errors into this lab. It's also the mass had to be assumed for the magnets, and scales were not provided, so the mass could have been off, leading to a different force due to gravity. Discussion is the two discussion questions we must talk over is the resistivity. If the resistivity of the conductor were reduced as close as possible to zero, what would happen? This would allow the current induced in the tube to be perfectly propagated around the loops of the tube when sliced, as talked about before. This would mean more current would be induced at lower voltages, which means that there will be at lower EMF rather, which would allow more magnetic field to be generated, pushing back into the bar magnet, leading to a slower drop. What if there are holes and slots cut into the tube? This would lead to some of the loops being destroyed and less current propagating back into the magnet as before, since they can't complete a perfect loop and generate a vector directly up into the bar magnet, pushing it straight back up. This would also lead to the bar magnet moving to the sides of the tube and not falling directly down into the tube, which could slow it down even further, which could lead to less magnetic force getting pushed back into the bar magnet.